So let's take a look at your in-class problem worksheet that you guys got on Tuesday. And we're going to look at number 3 on it. And it's the one that says a balloon with a mass of 0.08 kilograms is filled with 0.03 cubic meters of helium. So we have our balloon, it has a string on it. The volume of my balloon is equal to 0.03 cubic meters. It says that the mass of my balloon is equal to 0.008 kilograms. And it's filled with helium. What is the tension in the string? So what we're going to do is we're going to have a boy who's hanging onto that string. He's holding the string down. If he let go, the balloon would go flying up because there's enough buoyant force that it would take that balloon. So he's going to be holding that balloon down by a string, and that balloon's going to have, there's going to be some tension in the string. And that's what we're trying to determine. Okay? So ignore the part about how many balloons would it take to pick up Russell from the movie Up. We aren't there. So what other forces besides this tension and buoyant force are acting on the balloon? So the balloon has some mass. So we're going to have the Fg of the balloon. And we're going to take the mass of the balloon and we're going to multiply that by G. And that'll give me the weight of the balloon. Now, helium, even though it doesn't have much for density, it's relatively light, we often refer. It does have mass. So it also has some weight. So there is going to be the weight of helium in the balloon. And in order to calculate that, we take the mass of helium and we're going to multiply it by gravitational acceleration. Now, things listed, it gives us the density of helium of 0.179 kilograms per cubic meter. It gives us the density of the air, which is 1.29 kilograms per cubic meter. Now, we're hanging onto this balloon, so my acceleration is going to be equal to 0. So Newton's second law, the sum of all my forces is equal to mass times acceleration. My acceleration is 0, therefore my forces are going to be balanced. Newton's second law says I add my forces going up. My buoyant force up is the only force that's going up. I subtract my forces going down. The tension going down, the Fg of the helium, and the Fg of the balloon. All three of those are going to be subtracted. And we set that equal to mass times acceleration, which is 0, so we set that equal to 0. Now, we can go through, and we can do this in a couple different steps. We could go through, and we can go through and we can find Fg ahead of time and just plug in the value. That's what we're going to do right now. So the mass of the balloon was given, and the mass is 0.08. The gravitational acceleration is 9.8, so 0.008 times 9.8 gives us an Fg of the balloon of 0.0784 newtons. Okay. So that gives me this. I'm looking for tension, Fg of the helium. So I need the mass of the helium. This is one of those problems where I don't give you the mass of the substance, but I give you the volume of the balloon, and I give you the density of the helium. So what's in the balloon? Helium. If my balloon has a volume of 0.03 meters cubed, the amount of helium in my balloon is essentially 0.03 meters cubed. It's actually a little bit less because of the thickness of the balloon, but we can say that's pretty minimal. So we can say that the density of helium is equal to the mass of my helium divided by the volume of the helium we have. So 0.179 is equal to the mass of the helium in that balloon divided by the volume of the balloon. So then we cross multiply and divide 0.179 times 0.03, and the mass of my helium is going to be 0.00537. So I take that number and I say, well, the weight of my helium is going to equal 0.00537 times 9.8. So I take that times 9.8, and the Fg of my helium is equal to 0.052626 newtons. So I have these two Fgs. I'm just going to be plugging those two numbers in here. Again, solving for that tension. So now buoyant force. Hopefully at this point we know that the buoyant force is equal to the density of what's being displaced. So what fluid is getting pushed out of the way? The helium is filling the balloon. We fill the balloon is going to physically push the air out of the way. So we're going to put the density of the air in there. So the density of air is the density that's being displaced times the volume that's being displaced. So how much air gets pushed out of the way? Again, the balloon takes up this much volume, therefore that is going to be the amount of air that got pushed out of the way. Okay, so that's going to be the volume that was displaced times G. That's my buoyant force. Minus Fg of helium, minus Fg of my balloon, minus Ft, which is equal to 0. So start plugging numbers in. The density of air is 1.29 times the volume of my balloon, 0.3, times gravitational acceleration, 9.8, minus the Fg of my helium, which I already calculated to be 0.052626, minus the Fg of my balloon, which again, I already calculated to be 0.0784, minus my Ft equals 0. I'm going to go through for ease of things. I'm going to add Ft to both sides, and then it's going to be on that. This is going to come up with a number, 1.29 times 0.03 times 9.8 is 0.37926 minus 0.052626 minus 0.0784, which is equal to my tension. So you go through and you put those numbers in your calculator. And we get the force of tension of 0.24834 newtons. Okay, so that's how much tension is in this ring. Pretty small because my balloon is going to be pulling up, but it is going to have an effect. Now, the next part of this question is not talking so much about the balloon, but the fact that Russell, from the movie Up, 8-year-old boy, he's hanging onto a balloon. If we look at Newton's third law, according to the balloon, that tension is downwards. But if we look at the free body diagram of Russell, that balloon is actually going to be pulling up on Russell. So the idea is, if Russell has a mass of 30 kilograms, yep. So 30 times 9.8, he has a weight of 294 newtons. So how many balloons pulling up at 0.248 would we need in order to pick him up? Because every time we add another balloon, we're going to add another F(T) up, and another one up, and another one. So the more we add, the more we're going to get. So the idea is X, well, the sum of all my forces is equal to mass times acceleration. The acceleration is equal to 0. Okay, we're going to want to figure out how much is it needed just to pick them up. So X is my number of balloons times my tension from one balloon. Okay, those are my ups, minus the Fg is equal to 0. So I add Fg to both sides, and what I find is X times the number of balloons times the tension created by one balloon is that. So x times 0.248 is equal to 294. Divide by 0.248. Now I'm going to use the actual, no I'm not, I don't have that number anymore. So I'm going to divide 294 by 0.248, and I find that I'm going to need 1,185 balloons in order to pick Russell up. So is it possible? Yeah, it's possible. We just need a lot of balloons. So is it possible from the movie Up to pick up the house? Yeah, we just need a lot of balloons. Someone on the internet threw out the number. They calculated it based on the average square footage, the average balloon, the average weight per square foot of the house, how many balloons it was. And it was like 10,000, 20,000 some balloons. So that's just to lift it. They talked about trying to break the structure loose. That was another issue. But it is possible. So do people ever do this? You see in movies where they hand a clump of balloons to a kid, the kid flies away. Maybe not like that. Look up Lawn Chair Larry. Okay, look up Lawn Chair Larry. Guy from 1982, he put some other balloons in a lawn chair. He went for a little flight. Check it out sometime. Okay, but that's how we do that third in-class problem from that worksheet.